Hello everyone, welcome to the Materials Project Seminar Series. This series is co-organized by the Materials Project and the Materials Virtual Lab at UC San Diego. The MP Seminar Series are monthly talks from top researchers in the field, focused on topics of interest to the MP community. Examples including computational materials design, the use of MP tools such as the Parmesan Fireworks to perform materials research, and also the very hot topic nowadays, which is machine learning applied to materials research. During the talk, please use the Q&A button on the bottom to ask any questions. The questions will be answered after the talk by the speaker, or Matt and I can chip in for more generic questions. And for those of you who are watching a video recording, and you can ask your questions at our forum at mathscience.org with the Materials Project channel. So the recordings will be published to a few locations after the talk, including the Materials Project Seminar website as well as the Materials Virtual Lab YouTube channel. We're actively looking for speakers in the coming month, so please nominate the researchers that you like the most to our email list. The upcoming seminar for November will be from Dr. Artrith Nonok, and she's a new assistant professor at Utrecht University. For those of you who are interested in machine learning applied to chemistry and material science, you won't want to miss her talk because she's absolutely one of the experts in this field. We're still looking for December and January speakers, so please nominate your candidates. So today we have Dr. Kamal Choudhary. He is a scientist and founder at the Jarvis database and tools at NIST, and he is also a scientist at Theiss Research. He obtained his PhD from University of Florida in 2015 and then joined the NIST. His research interests are focused on atomistic materials design using classical, quantum, and machine learning methods. In particular, as I mentioned, he has developed the Jarvis database and tools that host publicly available datasets for millions of materials properties. And he's definitely one of the most active and established young researchers in the field. He has published more than 50 research articles in various reputed journals, and is also a very active member of the TMS, APS, and MRS societies. Unfortunately, Kamal is having some issues with the internet connection, so today his talk will be a pre-recorded video, and but he's also online for answering any questions. So again, please feel free to use the Q&A button to ask him any questions regarding this talk. Thank you.
Hello everybody, welcome. My name is Kamal Choudhary. I'm a research scientist at NIST, and I would like to thank the Materials Project Seminar Series organizers for giving this opportunity to present this talk. I'll talk about the deep learning and quantum computation methods for improved materials design. So materials design is actually quite an old topic. We have seen Mendeleev table and Dalton's atomic structure idea for more than 300 years. And the idea is if we take a bunch of atomic elements and put in a particular lattice or particular arrangement, what will be the property of that material, or the reverse way, we want this particular property, what should be the combination of my elements and what should be the arrangement of that elements and atoms. So this is actually a very hard problem. We can use something like many-body Schrödinger equation to predict properties, but it's actually very computationally expensive. We can use experiments, but it takes quite some time to prepare and synthesize the materials and so on, the trial and error method and so on. And so we have tried experiment, we have tried some empirical rules, we have tried computational methods such as density functional theory and other ab initio and molecular dynamics, etc. methods. And right now, I think we are in a very good time of having this data intensive age. So in this age, one of the key development is the deep learning and quantum computation. So we will see how can we leverage this really amazing progress in this field for materials design. So Today I'll talk about the deep learning and quantum computation, and especially I'll talk about three packages: atomistic line graph neural network, atom vision, and atom quantum computation or atom QC packages. These all projects are part of Jarvis, which is available at jarvis.nist.gov. And this is again a part of Material Engineering University at NIST. So the name Jarvis has some history behind it, but I'll not go into the detail. Rather, I would like to say that Jarvis, the name is inspired from a sci-fi movie. Okay, so moving on. Before I go into the details, I really would like to thank several collaborators and colleagues who, without help of whom this project would not be successful the way it is. So I would like to thank Francesca Tevezza, Kevin Garrity, Brian DeCoste, especially. They are the core members of the Jarvis team. In addition to that, I would like to thank other folks at NIST, and I'm only listing a few of them, and other collaborators at several national labs and universities. So this is my outline for the talk. I'll give the motivation behind doing this deep learning and quantum computation work, and I'll give a few slides on Jarvis infrastructure, and then I'll give around 10-15 slides on each of the aligned atom vision and atom QC, and then I'll conclude. So what is the motivation behind this work? So the idea behind this work is to really accelerate materials design using both computation and experiments. We want to automate experimental data analysis. There are ton and ton of data, so we don't want people to staring at it and analyze those data. We want to discover new material the way we want it. We want to develop new methods. We want to find new phenomena, interesting phenomena, and we want to enhance reproducibility. So there are several challenges for this work. One of them is high fidelity and diverse data and balanced data set. And when I say material science, we talk about the structure property performance relationship. When I say structure, it might mean different things. It might mean crystal structure, it might mean molecular structure, it might mean protein structure, it might mean microscopy images, it might mean spectral properties such as X-ray diffraction. So there are a wide variety of data set, and having a curated data set is really useful and the precursors for having a machine learning or deep learning techniques applications. Luckily, due to the Materials Genome Initiative launched by the former President Barack Obama about 10 years ago, such work of curating data sets and making data informatics models for machine learning for materials have really gotten along, and we are seeing rapid progress in this field. No matter what field or no matter what research areas are you working on, material science is a key component of it. So whether you want to make a better rocket or you want to make a better biological devices, you need a sophisticated material. So the idea is whether we can expedite this whole process. So I would like to start with this one slider on NIST Jarvis, which is available at jarvis.nist.gov. We recently have this user counting things. So it was started in 2017. The whole project started in 2017 using Material Genome Initiative. We have around 6,000 worldwide users. We organize this artificial intelligence for material science and quantum matters for material science workshops. We are getting nice feedback from the whole community. And right now, jarvis.nist.gov requires login. So please feel free to register. So Jarvis has several components to it, such as density functional theory, machine learning, force field, and other. And the code base is available at us.nist.gov/Jarvis GitHub page. And more details about it can be found in this NPG Computation Materials article. And as you can see, they have been downloaded and used multiple times. So as I said, we started in 2017. We actually started with Jarvis FF, Jarvis force field, to evaluate classical force fields or interatomic potentials. So for that, we used materials project at that time, the energetics and the elastic constant data to check whether a classical force field is suitable for particular applications or not. Then we saw that there's a need for the 2D materials database. So in 2017, we developed a lattice constant criteria, and then we use that for the materials project data set. And then we discovered around 1,000 new 2D materials. And we actually validated using exfoliation energy calculation using the opt-BD8 functional in density functional theory. So that was 2017. In 2018, we developed using this opt-BD8 functional elastic tensor database using the finite difference methods for 3D and 2D systems. We also saw that there is a need of better band gaps in DFT. So standard DFT underestimates band gap severely. So you want something which should be more closer to experiments and reality. So and higher level methods are more time consuming. So we wanted to find a middle ground. So the meta GGA, something like Tran Blaha modified Becky Johnson, was pretty useful. So we made a database for that. And in addition to band gap database, we also made a database of dielectric functions, frequency dependent dielectric function. In 2018, we also came up with this descriptor set called classical force field inspired descriptor, which can describe materials chemistry and structural information. In 2018, we also extended the Jarvis FF for the defect properties such as surface and point vacancies. In 2019, we developed this solar spectroscopic limited maximum efficiency, solar efficiency data set. And we came up with this spin orbit spillage criteria, which basically compares the wave function with and without spin orbit coupling to check whether a material is topologically trivial or non-trivial. And we applied for 3D materials for both metals and semi-metals. In 2019, we had a key point convergence paper with density functional theory and machine learning. In 2020, we applied this DFT ML hybrid approach for thermoelectrics and applied for 3D and 2D materials. And then we extended the topological spin orbit criteria for 2D materials for both magnetic and non-magnetic systems. We have a 2D heterostructure app design. So using the 2D structure database, we could predict the band alignment and the lattice mismatch, etc. We extended the density functional perturbation theory database from which we get the dielectric function, piezoelectric tensor, infrared intensity, and other key properties. We also developed this electric field gradient database from which we can calculate the nuclear quadrupole resonance and nuclear magnetic resonance spectra. In 2021, which is this year, we are actually working on Atom QC, which is the quantum computation package with variation quantum eigensolver and variation quantum deflation, which I'm going to talk about. Also, I'm going to talk about the Jarvis align atomistic line graph, which we applied to solids, molecules, and MOF and other materials classes. Atom vision, which is applied to scanning transmission electron microscopy and scanning tunneling microscopy images. Heavily focused on uncertainty quantification, as so many models are being developed. It's important to evaluate the uncertainty. And then we have anomalous quantum confinement effect, direct air capture using metal organic framework, one-year tight binding Hamiltonian database for both electrons and phonon. TB35 for 3-body tight binding models for more than 60 atoms and their binaries and ternaries. Density functional theory and machine learning applied to the topological spin orbit spillage criteria, which we applied to 3D magnetic as well as non-magnetic system. And we actually verified a few of them using experiment. And we are linking with the Optimate project this year. So we also already have an implementation of it for the FAIR principles of the data sharing. So these are only some of the projects. And as you can see, there is a rapid expansion of projects and growth in this field. And we are very glad to see this progress. In Jarvis, there are about 60,000 materials, 1,000 2D materials, and 60,000 3D materials, 110 force field, and more than 1 million properties. There are several papers for each topic, but today I'm going to focus on the 3 packages I'm going to talk about. But if you have interest in other projects, please feel free to look into. So whenever I give this talk about Jarvis DFT, I sometimes get this question, the similarity and differences between materials project and other data sets. So I'm going to just compare some of the properties with materials project. So we have to understand, or we have to realize that whenever we do high throughput calculations, we do have to take certain approximations and we do have to make some deliberate choices. So in this case, we Our Jarvis DFT uses the van der Waal DFT obviated functional and Traun-Blaha modified Becky-Johnson and DFT plus spin orbit coupling cases. And we converged the K point and cutoff for each material, and we converge on the energy and forces. So these are some of the key differences with materials project. They have materials project have more than 2 times of number of materials, but having such convergence and having more number of properties per material tend to make our database a little bit smaller than bigger database with millions of materials and so on. Currently, we have elastic tensor for around 17,000 materials, and we have gamma point phonons. We have piezoelectric infrared spectra and so on. We have dielectric tensor with and without ionic contribution. We have electric field gradient, Raman spectra, solar cell efficiency, topological spin orbit coupling spillage for distinguishing topological versus non-trivial topological materials, one-year tide binding database, and STM image dataset. And there are many others, but for sake of comparison, I think this would be serving the purpose. So before we do the machine learning or deep learning training, we need to have a data set already prepared for this. So there have been already several work for actually combining data set and making them interoperable. So that is fine, but for machine learning purposes, we want data set as a snapshot, and so that people can compare on top of it, not just continuously growing data and changing number of data points, etc. So we took a snapshot of Jarvis data set, which is DFT3D for the bulk material, DFT2D for 2D materials, Magnet, which is used for magnet models for materials project, and so on. There are multiple such databases, and this can be easily loaded in the Jarvis tools package, and then it can be fed into a machine learning or deep learning framework. So as I said, there are multiple databases such as QM9, etc. in this data set. Suppose we don't have such some properties, then we can get from the actual database from the Jarvis DFT, which is in the XML format. All the materials, around the 60,000 materials, have their own XML format data set. So we can parse this XML to get required information. So, so this is an active repository, and if you want to contribute your data set, please feel free to reach out. So let's talk about the atomistic line graph neural network, which is available at us.NIST/align repository. The preprint for this work is already available at archive, and this paper is also accepted in NPJ Computational Materials. So it should be coming out soon. Okay, so I wanted to point out that neural networks are very popular, so popular that they are making books for babies, which is quite interesting to me. But we have to keep in mind that when we do machine learning, we have to have at least certain level of understanding of linear algebra and calculus, without which there can be issues when we do actually machine learning training. We are working on a review article on deep learning for material science with folks from Materials Project, it was NIST, OQMD, folks from Carnegie Mellon, Northwestern, and Columbia. So this will be coming soon. And we hope that this will be useful for the material science community. So I'm going to give a very quick introduction how to use ANN, or artificial neural network, and graph convolution neural network. So for a conventional standard neural network, we have an input layer, input features, x1, x2. This can be, for example, this is your material and this is another material. You can describe them using an atomic number or average atomic number or average of electronegativity and so on. So this is your features, right? So you took these features and you know the output and you're trying to make a model that can predict this output. And we use this hidden layer, right? It's a very simple example, one hidden layer example. So any standard neural network will go through these basic processes. So first you want to make a forward propagation. So you have A0, in this case is X, or for L-1 layer, you take this input and then multiply with a weight matrix, and then add a bias term. So this gives you activation. And then with the activation, you put a nonlinear activation function, such as sigmoid, tanh, ReLU, CLU, leaky ReLUs. There are so many. And that makes it interesting. And sigma, the nonlinear activation function, is very important, without which the whole neural network is practically useless. So once you have these activations, we can write a cost function. This cost function will be a function of this weight matrices and the biases. And then we have the predictions from the neural network y tilde, and then we have y the actual target data, and then can make the cost function. Now there we can use gradient descent algorithm to minimize this cost with respect to the weight matrices and the biases. So there are various methods to do that. One of the most popular one is the back propagation rule, and which is based on the chain rule in calculus. So this is standard neural network. However, if we use this for something like an image, which is actually a matrix, here in the example of a 6x6 matrix, if you use a fully connected neural network, there will be too many parameters. So the idea of convolution neural network is to use convolution function and use a shared weights. So these are some of the key steps for convolution neural network. And these are especially used for the image applications or image classification and etc. So what we do here is we have a kernel or filter, a matrix. Here is a matrix here, and this is convolved over each of the blocks from the image, and then we can do element-wise multiplication and sum, and then we can pooling operation, either can be maximum, average, and sum, and then we use the what we have, the fully connected layer, standard neural network, to make a forward prediction. So this is convolution neural network. Graph convolution neural network. So let me talk about the graph a little bit. A graph is a entity will have nodes or vertices and edges, and the node feature matrix. So you can consider graph multiple way. It can be a social graph, it can be atomic structure graph, and so on. So for the atomic structure, you can imagine this this is an atom and this is another atom which are connected, but 1 and 3 are not connected. So this can be your boron, this can be nitrogen, this can be phosphorus, this can be another boron, and so on. So for each of this atom, we have a feature matrix such as its atomic number, its electronegativity, and so on. That is called the feature node features. And then we want to know whether one is connected to 2 and one is connected to 3, and so on. So that is given by the adjacency matrix. What is the adjacency matrix? It gives you the connections in the graph. So in this graph, 1 is connected to 2, so there is 1 here, but 1 is not connected to 3, so there is 0 here. 1 is not connected to 4, so there is another 0. 1 is connected to 5, so there is a 1. 1 is not connected to 6, there is a 0. So in this way, we form the whole matrix, and then there can be self-loop as well. So based on that, we get the adjacency matrix. So this is a very simple example of graph. Graphs can be of several types based on the applications. It can be weighted or unweighted graph, directed or undirected graph, line graph, heterograph or homogeneous graph, multigraph. So this is an example of unweighted graph because everything is 1 and 0. But in fact, if you can give the atomic bond length information instead of 1 and 0, like 1.2 angstrom and 2.3 angstrom and so on, that becomes a weighted graph. It can be a directed or undirected graph. So 1 is connected to 2, that means 2 is connected to 1. So this is a kind of undirected graph. But suppose you have a Twitter follower. So you are not following him or her, but he is following you or she is following you. So that is basically an example of directed graph. So there's a directional component to it. There can be line graph, which I'm going to talk about. There can be heterostructure or homogeneous graph where we have multiple type of information. And there can be multigraph where we have multiple connections between nodes. So we described adjacency matrix, which is a nodes by node size matrix. And the degree of a node is basically how many connections each node has. And basically the idea is you have the input feature. You represent this input feature and you put in a graph embedding. And then we want to make a representation of the node so that it best describes the system. And we update the node representation. And this process is basically extremely efficient on GPUs. So the idea is we take this input matrix X, or in this case, H0 or L equals to 0 is this. We multiply that with the adjacency matrix, which we just described here. Then we multiply that with a learnable parameter W weights. And to make it interesting, again, we put a nonlinear function. So this gives us the HL plus 1, the next layer representation. So yeah, and the graph works locally, so this is great. So that's why it's very efficient in GPUs. So this is just the matrix representation. You can also represent using the vectorial representation. So for each ith node representation, we have the jth contribution for all the neighbors of I, and this f is called propagation functions. And based on this selection of f, there can be different type of graph convolutions, such as graph sage, graph convolution, and many others, many others. We use align here, for example. So this is a one slider introduction to GCN. If you want to know more about the graph neural network, I will recommend to go through this paper on benchmarking graph neural network, and the code is also available from this Yoshua Bengio's article and the GitHub link. Okay, so a little bit unpacking it, the graph convolution from material scientists. So here is an example for barium titanate, which is made of, again, the titanium, barium, and oxygen. We first define end input dimensional feature vectors. So titanium can be represented by its atomic number, its atomic mass, its electronegativity, for example. So that's 3 features. Similarly, we have barium, another 3 features, which is different from titanium and oxygen. And then we also hot encode them, and then we can have multiple features like atomic melting point and so on. That gives the node input feature. This is very similar to what we do something in traditional machine learning processes. So that is that part is, I hope, is clear. But then the idea is we have to use the node embedding. So once you have the node input atom feature vector, we embed this on an atom embedding, and then we take into account the atomic distances using this kind of representation f here, where you can consider this actually very similar to an interatomic potential, where you have elemental information and the distance based information, cutoff and other stuff. So generally in an interatomic potential, you will make a parameter, you'll try to optimize for parameters, but here you let the neural network, graph neural network, decide this automatically. So what is a graph embedding? This is a graph embedding is a way to encode high dimensional data into a low dimensional space. And so we do put all the HI on the input feature vector on a atom embedding, and this will be the edge embedding, which is basically the distances. And in this case, for 5 pair, we element wise we concatenate this one, and we use the RBF radial basis function on the distances, and then we use something like gating function that gives the importance of each edge. So it's so that there is some anisotropy in the graph can be captured. So again, it's very similar to the interatomic potential idea, just in a graph neural representation. So with that, a few more words on edge-gated graph convolution. So it's based on the this repository on graph deep learning, and as you can see, we have the source node data and the destination DST, the destination node data, and these are applied in the deep graph library. So DGL is a fantastic library for handling sparse matrices, for example, and they have several inbuilt functions to work on graphs. So once you have a graph in the DGL format, you can apply methods such as update all and apply edges and so on, which to do the message passing automatically, and then you can use something like nonlinear activation. So in this picture, what we have, the node, ith node, and the corresponding j neighbors, and the edge features, the distancing and so on, we can kind of concatenate them. And we have a gating matrices. And then we applied a CLU kind of nonlinearity, and then we sum it up to kind of get the next layer representation. So this is one of the graph convolution. We can use multiple others, but this is probably was most compelling when we are trying to make this formalism. So before I go to the align thing, I want to talk about the line graph. So a line graph can be considered as a graph of a graph. So we tried multiple methods to capture the angle information in a graph. So one of the method is you take the first nearest neighbor cutoff and you try to capture all the angles within this first near neighbor for each atom and use this as an edge feature. That's one approach. Another approach is you can take an atom and count the partial angle distribution function around each atom and use this as a node feature. So we tried multiple such methods, but it didn't work out very well. So then we read about this line graph neural network idea, which is pretty interesting. So what happens in line graph is, suppose this is my ith is the edge, and j, so I is an atom, node atom, and j is another node atom, and this ij is an edge. In a line graph, this edge becomes a node, and this edge becomes a node. So any feature will be the angles, right? So that will be a three-body term. So a line graph is a graph of graph where nodes are the edges, and the edges are uh, the bond pairs, for example. And for node feature, as I described, we have the something like electronegativity, atomic mass, atomic number, and so on that describes the node. And the edge features are based on the interatomic distance with a radial basis function. And then we have triplet features, which is the radial basis function of the angles. All right, so once we know the line graph, we can go to the align model, which is a bunch of graph and line graph models. So, and it has multiple align and edge-gated graph convolution. And we have initial atom, bond, and angle features, which goes through this multiple set of edge-gated graph convolution and align layers with a graph and line graph. And then we do feature-wise sum across the atom, and then we predict properties. Here is a code snapshot. So here I'm showing you that how the align model has atom embedding with atom input features and edge embedding and angle embedding with RBF. And then we go through multiple graph convolution and align layers. And then we do average pooling that I discussed before. And then we do a very simple linear models to predict properties. So example of this is also available on the GitHub page. So in this example, we train for 50 materials, but you can expand to whatever number of materials. What we give here is we give a root directory where we put all the position file. It can be POSCAR or CIF file, but here example, we give POSCAR files. So we put all the POSCAR file in a Excel sheet with the ID names and their properties. It can be single output or multi-output, classification or regression, and then we give some certain hyperparameter configuration here, and that trains the model on using GPU and Google Colab. So we try to compare some of the properties on the materials project dataset, which is, I think, one of the most well-curated datasets in this community. So with the 2019 dataset, we have 69,000 materials, which is also used in the Shannet and Magnet kind of papers, which had formation energy and band gaps as a target. And we had the mean absolute deviation, which is the average predictive model or the baseline model. And then we have the classical force field inspired descriptor model, which is a descriptor or handcrafted descriptor model. Then we have CGCNN, Magnet, Shannet, Align, and models. So we clearly see that Align is outperforming other models, and especially for the band gap data. So there are two interesting things here to notice. First is the mean absolute deviation versus mean absolute error is really high for classical quantities such as formation energy, but not too high for the band gap. So usually you want it more than 5 MADs to MAE. We see that this is generally more than 5, of course, but for electronic band gaps, it's not in the order of 40s and so on. However, we notice that using angle information, we have decreased the MAE, mean absolute error, on the band gap model substantially. So this shows an interesting behavior that actually including the material science knowledge, domain knowledge, in the deep learning is not too bad an idea. Usually deep learning experts would tell you that do not use any domain knowledge and all the data will be learned automatically. But here we suggest here that using domain knowledge is actually useful and can be used to make reasonable predictions. So this was the performance on materials project datasets, 0.02 and 0.21. So we also tried this on the Jarvis DFT dataset, which has 55,000 materials, around 14,000 materials less. So we see that the formation energy is higher, MAE is higher. Again, because we have around 14K less materials. But interestingly, our band gap MAE is 0.14 versus 0.2 in the previous slide. So this can be due to the different density functional method used, or there can be several reasons or different convergence criteria and so on. So what we want is basically we want something on the order of 5 uh, order of magnitude less than this. Then hopefully we'll be reaching our deep learning chemical accuracy model. That will be kind of a goal. If you can lower this 5 times more, that will be really interesting. And then hopefully we'll be able to make more reasonable predictions. Also, we notice here, in addition to formation energy and band gap, we trained multiple models such as solar cell efficiency, magnetic moment, topological spin orbit spillage, etc. Around 50 models like this, and it does really well for the energy-based quantities, and not too well for the electronic quantities. So this is interesting. We also applied this model on the QM9 dataset, which is a molecular dataset, and we kept the same number of parameters as solids. And the QM9 has around 130K materials. So one interesting thing we notice is that Align model outperforms all the previously known graph neural network models such as DimeNet, ShunNet, OrbNet, etc. And especially except these two targets, highest occupied molecular orbital and 0-point energy, Align can outperform all the other properties in this table, at least in the QM9 dataset. And so that is interesting. And so it says that our model can be used for both solids and molecules. It was a long, tedious process to get the hyperparameters. So we first tried a bunch of parameters in the Align model. Then we did use the rate tune to get the final parameters. Some interesting thing we noticed that we had to use something like one cycler, scheduler, and CLU kind of activation function, which is slightly different from other graph neural network models. And we also use the DGL framework, which makes our model really, really faster compared to others. Okay, so layer ablation study. Any deep learning should have this component. So we want to know the align and GCN layer. We saw that if you use at least 2 GCN and 2 align layer, we get reasonable performance. This is the Jarvis DFT formation energy ablation study. And similarly, we use around 200 hidden features. Then we get a reasonable models. And we did several ablation study for other components of the align model as well, which is available in our paper, but you can look into it if you're interested. Another important component is a training time study. So one way to compare timing for model training is the epoch per minute or time per epoch. So we have Align, Magnet, ShunNet, DimeNet, DimeNet++, CGCNN, and models. So we tried the QM9 U0 model, and then we see that time per epoch for Align is comparable to other models. However, I would like to point out that although the time per epoch could be 6.8 versus 3.4 or 3.0, the total number of epochs to reach the desired accuracy can be different. So in this case, Align will reach the accuracy in 300 epoch, but other models might take 3000 epoch. So in the longer run, Align can be faster. So this is something interesting to note. I will not go into details of the application Align here, but because of the time, but I would like to point out a few brief applications. So one interesting topic is AI for climate change. So one of the particular application is carbon dioxide capture using metal organic framework. So metal organic framework can be considered as a metal ion organic linker material, and we have several databases of metal organic framework. And metal organic framework basically captures CO2 in these pockets. And there are our pores, and there are materials such as zeolites, which are traditionally used for carbon capture, but metal organic frameworks are extremely promising because of the high functionalities. And there have been databases such as HMOF, hypothetical MOF, Metal Organic Framework database, which has around 137,000 MOF materials, and they also provide nicely the grand canonical Monte Carlo simulation for CO2 adsorption. And in fact, this GCMC for CO2 adsorption compare well with experiments. So using a 80-10-10 training, validation, and test split, again, we try to predict the multi-output model for CO2 adsorption at different pressure. So these are the 5 best and 5 worst predictions. So again, these are the 5 bottom ones. So you can even the best one are definitely good, really good, and the worst one also, they have good trend, and they are not systematic, but some of them are high, some of them are low with respect to the grand canonical Monte Carlo. So after we trained this model on HMOF, we actually tried this model on other MOF datasets such as core MOF, and we then screened the best few MOF from material that can be synthesized that our experimental collaborator can grow in lab and test this deep learning guided screening and so on. So in addition to this, we can screen materials such as solar cells, piezoelectric dielectric materials, topological materials, thermoelectric materials, and so on. We have done this work with CFEED model, but we can definitely do this with Align model. So this was atomistic line graph. Let's go to the Atom Vision model, which is a deep learning framework for atomistic image data, which is available at us.gov/atomvision. So there we have 2 types of data: scanning tunneling microscopy images and scanning transmission electron microscopy images, especially for the 2D materials. So we use the STM Terse-Hammond approach with constant height and constant current images. So the Terse-Hammond approach is based on the idea that tunneling currents is proportional to the IL-DOS, or integrated local density of states, which can be computed using the density functional theory. And here's an example for 2D materials, and these are especially suitable for 2D materials because they don't have much dangling bounds. In the first and third column, we have the simulated images, and the second and the fourth column are the experimental images. And you can see they compare really well for the STM images. And this was published in the Nature Scientific Data paper journal. And similarly with STEM, we use the convolution approximation, which is a basic approximation and can be used for thin films such as 2D materials. The convolution approximation is based on the Rutherford model of scattering. So where Z, the intensity of scattering, is proportional to the Z square. But here we use, because there are a lot of other losses, we use 1.7 or 1.4. So using this model of convolution approximation, we can simulate STEM images of the 2D materials. For general materials, we'll use multi-slice, but for this multi-slice simulation, which can capture phonons and other contribution, but for 2D material, this should work well. And we actually see that in the examples for comparison to experiments such as graphene, iron telluride, and molybdisulfide. The STM and STEM, this is the experimental, and first and third column are experiments, and the second and fourth columns are simulated images. They compare quite well. So one of the tasks we want to solve using this image data set is the 2D classification. So this is very similar to ImageNet or other image classification models, such as classifying cat and dog and such, and some other classes. So here we want to classify whether a 2D material is what kind of Bravais lattice there are 5 possible Bravais lattice in 2D materials: hexagonal, square, rectangle, rhombus, parallelogram, etc. Usually during experiments, we'll use a Fourier transform of that image, and then we can, based on that, we will tell whether what kind of lattice it is. But it can be cumbersome when we have thousands and thousands of images, and rather we will give it to the machine vision or torch vision kind of packages, so that it can automatically identify the lattice. So that's the goal here. So once we have the STM and STEM image data set for thousands of 2D material that we develop, we use this pre-trained models such as VGG, GoogleNet, ResNet, and ShebNet and DenseNet models, which is available in the Torch Vision package, and trained on multiple and thousands of image data. And we apply this on the 2D STM and 2D STEM image data set, and we get more than 80% accuracy. So we notice that the baseline model for this performance should be 20%, so 1 over 5, 20%. So our model is doing about 4 times better than the random guessing model, which is actually very promising. So this is the image classification task. If you want to train using a Google notebook, this is an example given here in the Atom Vision repository, where you say what kind of model you want to use. For example, DenseNet. You give the training folder where you have all the images with the class, like 0, 1, 2, 3, 4 for 5 classes, and the test folder, and it will do the training for you. Even if you don't know much Python programming and so on, you can use it. Okay, so Atom Vision example. In addition to classification, we can use something like feature extraction and semantic image segmentation applications. So here's an example for MO vacancy and MOS2 and iron vacancy and telluride. So what we can do is we can detect using something like Huff circles where the atoms are, or some other models, and then we can construct atomistic line graph, similarly what we described in the earlier model, and then we can predict properties directly. So that will be something very useful for the experimentalist, I believe, because our huge TFT data set will no longer be a standalone in its own world. It will directly link to the experiment, so that will be very useful. This is still an ongoing work, and we are very excited about it. So this was Atom Vision. Let's talk about Atom QC, or Atomistic Calculation on Quantum Computers package, which is again available at us.nist.gov/Atom QC. And here's Google CEO with right next to the quantum computer machine, well, a model of it. So Google's recently claimed quantum supremacy, and this is another very exciting technology that has come along. And this technology has been mainly applied to molecules, small molecules, with a couple cluster kind of methods. And we wanted to see whether we can use this methodology or this quantum computation method for solids, or how to use this for solids, where we have periodic boundary condition. So I'll give a very brief introduction to the quantum computation here. So in a quantum computation, well, current state of quantum computation, we have one of the major algorithms is variation quantum eigensolver. So in any chemistry problem, we are trying to find the energy level of a Hamiltonian, right? So what VQ does is actually a hybrid classical quantum algorithm, and you take a Hamiltonian and choose a particular ansatz and circuit with trainable parameters like theta 0, and we feed it to the quantum computer. So we notice the quantum computers are good for preparing quantum states. So once we give this, and then we get the expectation value, and then it feeds that to a classical optimizers, because quantum computers are not very good, and at least currently they are not very good at classical optimizing the parameters. So in this hybrid loop, we keep ongoing this loop until we reach desired accuracy. You can find more details about VQE algorithm in this Nature Communication article. And so this again gives you the ground state eigenvalue and eigenfunction. How about other eigenvalue and other eigenfunction of the qubit Hamiltonian matrix? So for that, we can use something called variational quantum deflation algorithm, which is actually a very simple idea, that once we know the ground state eigenvalue and eigenfunction, we can deflate the whole matrix and get the high level energies. So I want to make it clear that these are not the excited state, like we talk about many body perturbation theory and other excited states. They are just within the same theory, but non-ground state eigenlevels. So I want to make that clear. So if you use something like classical computer for a small system, this is very, very fast. But for quantum, it's just a proof of concept, and we'll be testing for a few solid materials in this particular work. Here is a typical flowchart of how to use quantum computation on atomic structure. So we use one-year tight binding Hamiltonian. So once you have atomic structure, we can use DFT plus 1-year 90 or finite difference and density functional perturbation theory for electrons and phonons respectively to get 1-year tight binding Hamiltonian representation. So a one-year function is a complete orthonormalized basis set, and it's actually a very good bridge between the delocalized plane wave and the localized atomic arbiter representation, and most of the DFT cores actually support one-year function generation. So once we have the one-year function, and we have the tool in the Jarvis tools anyways, so you can look into it. So once we have that one, we can convert that one-year tight binding Hamiltonian to a 2 by n by 2 by n matrix. So we could use here the same like plane wave basis, which will give us something like 20,000 by 20,000 matrix, which is huge for current quantum computers. So that's why having a one-year tight binding representation is very helpful. All right, so once we have this n qubit matrix, we transform it into a Pauli basis, and then we feed it to quantum circuit, which I'm going to talk about. As we said, we'll use the variation quantum eigensolver and the variation quantum deflation to get all the eigen values, and then we feed to something like green function with a zero self energy, and then feed it to impurity solver to get the actual green function that can predict the something like band gap very accurately. So this is a typical flowchart, and this is published in the Journal of Physics Condensed Matter this year. So one of the key differences of using the classical versus quantum computers. So we can go to our classical computer like laptop or something, and then maybe make our arithmetic operations, sum, multiplication, etc. We don't need to think about the circuits which it is using. However, for quantum computers, we do have to consider this. For each problem, there's a specific circuit that we have to use, or answers we have to use. So these are some of the 6 circuits that we tried. So circuit 1, circuit 2, circuit 3 is for 3 qubits, and it's based of RY gates and RZ gates. And as D, E, F are known as real amplitude poly 2 design and efficient SE2 circuit. And they have, in addition to RY rotational gates, they have the controlled X0, controlled X and Z gates. And we will see how these circuits perform for predicting the eigenvalues. So we take a very simple example of aluminum, right? So we want to predict the aluminum gamma point energy level for electronic one-year tight binding Hamiltonian. And we see that all the 6 circuits actually do pretty well for predicting the eigenvalue. But when we go to the X point, which is non-gamma point obviously, only 4 and 6 circuit, which is the real amplitude and efficient FC2. They are the only circuit which can get the eigenvalue correctly. And if we go further, like a multi-component system and so on, we see that not just one repeat unit, not just one repeat or unit of 6 circuit, we have to use multiple repeat unit until like 4 repeat unit to get the eigenvalue correctly. Here is an example. So for a given material such as aluminum, you can get the one-year tight binding Hamiltonian from Jarvis, and then get an HK for a particular K point. And then we have made this Hermitian solver class using Qiskit that will solve the Hermitian matrix and using VQE and for a particular circuit. So here we are taking circuit 6, and you can take something like state vector simulator or QASM simulator or other quantum computers, and that will give you the classical VQE, classical and VQE eigenvalue that you can compare. All right, so in addition to Qiskit, we can use something like Tequila, Open Fermion. There are a few more, Penny Lane, etc. in addition with a similar idea. Here's again a complete example of aluminum. So in this left-hand side, we have, as we mentioned, the VQE is a classical quantum hybrid algorithm. So there are different kind of classical optimizer. So we compare this for aluminum band structure, aluminum X point one-year tight binding electronic Hamiltonian, and we found this Kobila and SLSQP probably are the better ones for classical optimizer. Once we select that, we actually use variation quantum deflation for predicting the whole entire one-year tight binding Hamiltonian based electronic band structure using VQD and the exact NumPy solvers. They agree very well. And we had to use at least 5 repeat units consistently of this, the circuit 6 model. And we can get similarly much in a good agreement for the phonon band structures. So that was the example of elemental system, but we applied this for thousands of other 2D multi-component systems. So to limit the computation in the quantum computers, we limit ourselves to an n qubits 5 qubit system. And then for that, we get the phonon and the electronic 1A tire bending Hamiltonian for 930 and 300 materials respectively. And we are trying to predict the gamma point energy levels. And you can see they agree quite well with the NumPy solver and the VQE solver. So this is very interesting. Also, we noticed that we had to use the efficient ST2 circuit throughout the entire material set. We are trying to extend it to the dynamical mean field theory. I think this is probably one of the most interesting applications of the quantum computers. So dynamical mean field theory is a commonly used technique for solving predicting electronic structure of correlated systems. And it maps a many body lattice to a many body local problems. In DMFT, we have HK that we can get from the VQD, or Western constant deflation, feed it into this equation with sigma 0, right? And then we can calculate the spectral function and the hybridization function that can go into something like a quantum impedance solver, and we can do it multiple times to get the sigma, the self energy that if we add to the Green function, we can get the accurate band structure, etc. So this is still an ongoing work. So in conclusion, I would like to point out that NIST Jarvis database has thousands of materials, properties, etc. It's an open access platform, so please feel free to contribute. There's a lot of opportunity in this field. I would also like to point out that some of the future works we are interested, such as using atomistic line graph with classical force field, or tide binding would be very interesting as a hybrid method. Having the implementation for the quantum computers with impedance solver will be very interesting. Using the images as a graph neural network will be very interesting. So there are several new ideas which are coming along, and hopefully next time you hear me, we'll have some updates about that. And these are again some of the links. And if you have any question, please feel free to reach out. Pretty quick with emails, so I hope I'll reply you early. And you can find more details on the computational material science, NPG computational material science article here. And with that, I'd like to thank again to all of you for attending this talk, and organizers from the Materials Project. I think this have been really great for me. So yeah, thank you.
I'll be happy to answer any questions.
Yeah, thanks, Kamal, for the great talk. Now we are entering the Q&A session.
Selects it. There's no change. It selects 5 extra K points, extra point to check whether it's actually converged or not. And then if it is, then it decides, okay, this is a converged quantity. And I want to point out that we are converging only on energy if we do a sophisticated calculation for one particular material, like old-fashioned style, when people used to do PhD on one particular material. You will converge on different, like its energy, its forces, its other properties. But here we are only converging on the energies. Okay, and then can you elaborate on the conversion and how does it influence computer probability? So I personally found that especially for properties such as phonons, elastic constants, dielectric tensor, magnetic moment, these are extremely critical. And again, I'm saying that although we converge on the energies, our convergence seems to do much better job on predicting those non-energy quantities as well. So that's what interesting. Hopefully that answers your question. Next question is from Philippe Torres. He's asking, what is the role of node self-interaction in graph neural network? Right. So maybe I missed, if I understand your question correctly, we have the identity matrix, right, that we described. And then with the A, we have identity matrix. So with this identity matrix, actually consider the interaction of the node with itself. So A plus I is A tilde. I think I didn't describe that one. So that is very important. Else you'll miss the interaction of the node in feature itself. So that is important. Hopefully that should answer the question. Okay, so what was the next one? Has anybody used deep learning or machine learning method in connection with supercapacitors? Supercapacitors, I am not familiar with it. This field is rapidly expanding, so I can't keep track of it. But hopefully, if you are expert, please look into it. And okay, so I don't know on the top of my head any work like this. Is the comparison made with experimental data or MP only? Okay, so so there are two parts, right? So first is for usual making the database part, we compare the small chunk or small subset with experiments wherever applicable to get the error bar on our prediction of the entire data set. But of course, this is not possible for all the materials, and if you are thinking about the error on the machine learning part, so what we do is we take the entire data and we split into 80-10-10 training, validation, and test split, and we train on, for example, 80% and then valid and use it on the validation and test set. So in this way, we are not directly comparing to the experimental data. Hopefully that answers your question. Okay, so another question is from Kerry Wrighton Aranida. So fascinating. The application, thank you. The application of these new techniques to resolve materials research is awesome. I agree with you completely. Is it possible to use graph convolution to propose new crystalline structure based on molecules as starting point? I mean, if Jarvis can develop a conformational search to find set of minimum energy conformation, then to use this as a set to propose possible crystal structures and the electronic part. I'm glad to see this presentation. Thank you. So there are two components to this question I see. First, you can do a starting search, kind of a new crystalline material. So there have been methods such as genetic algorithm and USPECs and all these methods where you can take parent structure and kind of make these structures and let kind of this deep learning or machine learning model guide the process. So that is one way of generating new structures and new conformation. Another way is, which I'm actually very interested, and actually I'm working today on this, is the generative adversarial network, GAN, and variation autoencoder. These are really fascinating techniques. It has certain limitations to it, but using this technique also, given a particular property and given a kind of starting conformation, you can find what will be the next possible material. So these techniques have been applied for molecules, and for solids, it's actually very difficult. There have been like voxel kind of techniques and some other techniques, but using the graph, it's actually quite difficult, but we are trying to work on it. So great idea, we are working on it. Isaiah Moses is asking some question. If if bond distances and bond angles have to be calculated to get the features, it means I need to know my structure completely. Yes, that is true. What is the advantage of machine learning then? Since electronic properties like band gap and formation energy with DFT might not be more expensive than the calculation that had to be done to obtain the features. Wait, so let me just step back from there. So even if you know atomic structure, like ICSD, you cannot tell what will be the band gap of that material, right? So you have to do like DFT calculation, which takes a long time, etc. So this is where we are saying that if you have experimental structure and you used to use something like density functional theory, something to predict property, instead of that, we can use machine learning to predict properties with certain limitations, of course. So that is the whole idea. So in this way, I have to disagree with you a little bit, but again, the idea is to predict the properties directly from crystal structure. I also want to point out there have been few works where we actually don't have to know the whole crystal structures completely, and then also you can predict properties. I have seen some papers like this as well. So if you're interested, feel free to reach me out. I can send you the papers. Okay, next, Anonymous. For the crystal graphs, how do you define starting edges? Nearest neighbor, how do you deal with the periodicity? Do you build graph over supercell or unit cell? Okay, I apologize, I forgot to mention the details about this. So as you rightly mentioned, we take k nearest neighbors, we take 12 nearest neighbor around each atom, right? And if the unit cell only have like 2 atoms, it of course doesn't have 12 nearest neighbor. So we will build the supercell in the image way. So it will know what image to get the atoms from. We actually do not build the supercell. There is a hypothetical image kind of thing you can make and get the atomic coordinates of the neighbors, and this is how we do it. You can find it in the repository. If you go to the README page, I think I describe it there. Yeah, these are all bond distances and k nearest neighbor. Okay, Isaiah asked another question. Maybe improving on composition-based features might be better for electronic properties at least. Yeah, I agree with you. So, this is something I really want to look into it, but just don't have the bandwidth right now. So I want to do a combinatorial search so that we can have certain features and atomic numbers and other hot encoding versus not hot encoding and so on. And then hopefully this will, so electronic properties are really bothering me. I mean, this is something really bothering me. We can't get the band gap model so well. So this is something to look into as well. So one thing I also didn't point out, in addition to the note feature, we can think about the dihedral angle, which we actually do not consider explicitly. So maybe in a different model, in addition to the bond distance, bond angle, and we also include dihedral and other n body, because line graph can be extended very easily. So hopefully using that, we'll be able to solve this electronic property problem. But again, it becomes very complex and expensive. So we have to think carefully how to do that one. Okay, anonymous attendee, except for 1 year, are there other bases like natural orbitals available in Jarvis? Great suggestion. Yeah, I really want to add other orbitals also, but currently we have only 1 year orbitals. Great suggestion though. I'll keep in mind. Okay, Bala Ramachandran, can you talk? Can you talk a bit more about strategies you are using to correct DFT band gaps? So right. So we are right now using the MetaGGA Tran-Blaha modified Becky-Johnson potential, which is actually very good, especially for non-correlated systems. And we are doing that. And we also have a database for hybrid functionals for like, I think 200 materials, and Tran-Blaha modified Becky-Johnson for I think 17,000 materials. So this is one of the strategy. We have actually tried other functions like scan and stuff, but we are actually quite happy with the TV MBJ, the way it works. So yeah, that is the strategy we are attending. Anurag Udome, he's asking, in comparison, how faster of two methods between GCMC and your DL model, and please explain a bit why. Okay, so GCMC is faster, it's based on force field, but I would say deep learning model is like maybe 100 times or more faster. So what happens in GCMC, you have to know the force field first, which is again, it's a whole new game. I'm not going to there, but you have to have the particular force field for your grand canonical Monte Carlo. You have to develop that. Once you develop that, you have to run the GCMC calculation, which takes around maybe 20 minutes per mock or something like this. But if you use graph convolution, you have atomic structure, and within maybe 5 seconds, it will predict the properties. So definitely much faster. Okay, Robert. Oh, hi, Robert. Kamal, very interesting work. What is your favorite DFT code for this work? Were you able to integrate? Yeah, okay, so there's some interaction I had with Robert. So right now I'm in tied to WASP. Mainly, we also have a quantum espresso database coming along. Kevin Garrity, he's doing that in our group. So we don't have integrated the NWChem yet, but yeah, we might think into it. Okay. So Felice Karakos Basak, is this method only valid for 2D materials? So wait, this you mean the image, I guess you're asking. So the STM and STEM image generation is the kind of method we use. We are using only for 2D material because it doesn't have dangling bonds, but you can use for like aluminum oxide or other surfaces. But again, it won't be very accurate. You have to use something like multi-slice simulation and stuff. And also you will have to use something like different tip in STM. Right now we use S-Wave. You can use something like Bardeen method and stuff, etc. for STM. So works really well for 2D material. That's why you are using it. But the method itself is not limited. Okay, there's one more question. Bhupesh Bishnoi, very interesting talk. Thank you. If I'm correct, the property of material come from the orbital SPDF interaction. You are right. So by looking at bond length, angle, or even lattice packing density will give type of material like metal, semiconductor, etc. So I'm thinking, can we use in graph neural network orbital information for operating electronic property? Do you have any comment? So yeah, there have been few works about this. I think I saw this paper on OrbNet, which I think used the orbital information. And one of the member of the Jarvis, the Kevin Garrity, he's also interested in this kind of orbital interaction. So yeah, so this is something we'll look into it in future. Okay, so the Claudia Copics, if edges are only created with nearest neighbor, doesn't it impair the performance, e.g. aromatic system where the electronic structure is bigger than just a few atoms? So okay, so I don't have background to say what does it do with the aromatic systems, but we try to capture the distance as well as the angles, right? The directionality. So using that information, I hope we are capturing all the necessary chemistry, like how we distinguish different molecules. So yeah, I don't have a great answer for this one, unfortunately.
Yeah, so great Q&A sessions. We still have about 70 participants who are still staying with us till the end. That's really impressive. So yeah, again, thank you so much, Kamal, for the wonderful talk and also the great Q&A session. And for those of you who still have other questions, feel free to ask on the materialscience.org and the Materials Project channel. And maybe Kamal can hop on and answer some questions about the talk. Yeah. Thank you so much.
Sure. Thank you, everyone.
Yeah. Bye.